and welcome to our last day of the training session. And today we'll be talking about AGN. And originally in the program I had thought of classification. I will do a little bit of classification, but I also wanted to do something which I thought would be more interesting to the others, which is about estimating the black hole mass of AGN. So I'll be first doing that, and then I will then continue with a little bit about classification. Yeah. So today we are talking about AGN spectra, black hole masses, and a little bit of classification, like I mentioned. So what are active galactic nuclei? Now, active galactic nuclei is that in the center of galaxies, you often have a massive black hole, which a massive black hole essentially means 10 power 6, a million times the mass of the sun, or supermassive black holes, which are there in the center of galaxies. And these are compact regions of the galaxies, which have a very high luminosity, and they radiate in the radio, in microwave, in infrared, in optical, in X-ray, gamma rays. And galaxies which host this kind of a phenomena, this active thing, is called an AGN, or an active galaxy. Now, non-stellar radiation is, so this, other than the radiation which you get from the stars which make up the galaxy, you also get radiation from accretion of matter onto this supermassive or massive black hole, which is sitting at the center of the galaxy. Now, even if we look at our own galaxy, the Milky Way, we know that the galactic center is in the direction of Sagittarius, and essentially it used to always be very difficult to observe this region of the galaxy, because this region had a lot of gas, right? So especially in the optical bands, if you looked at the galactic center, you couldn't see anything because of the amount of absorption. And but it was, there have been studies which have shown since a long time that there is a massive black hole. That means a black hole of about 1 million times the mass of the sun sitting at the center. The early estimation was about 3 million solar masses is the mass of that black hole. So many of you all would be aware of the Nobel Prize, which was just given 2 years back to this trio, and this trio basically got it for black holes, for the discovery of the supermassive black hole in the center of our galaxy. So Roger Penrose basically did theoretical work on this, while Genzel and Ghez, these two teams which worked independently, they actually collected observational data to study the supermassive black hole that's at the center of our galaxy. So if you actually look at the region of Sagittarius, this is the galactic center, and this is an image, the VLA image. This is in radio. You can see that this Sagittarius A, this is approximately the area of where you expect the galactic center to be. And here you have a set of stars which are, closer to the galactic center, where you have Sagittarius A star. And basically what the team of, like I said, most galaxies have supermassive or massive black holes at the center. So what was actually done is there was very, over a very long period of time of more than 16-20 years, this star S2, which you can see over here, which is close to this region, you basically have this star which was actually very closely monitored. It's close to that radio source which I just showed you, Sagittarius A star, and S2 is a star which is close to that. And what was done is, this is the star somewhere over here, and what you can see is that this was monitored over a very long period of time using infrared observations to actually derive the orbital parameters of this star. And this star is very close to the galactic center at a distance of only about 17 light hours. And what was done is, the closest approach was in 2018. And this was actually done to make a very good estimate of the orbit of this star, so that they could estimate the mass of the black hole which is sitting in the center, which was driving the motion of this star. And that's exactly the work that Andrea Ghez, her team at UCLA, that's what they were involved in, where they studied this in real detail. And this being a women in astronomy thing, I wanted to speak more about her work than the others who got the Nobel that year. So here's the S2 star, and like you see, these are all the data points which they had for the thing, with which they actually found out that S2 was moving at a very fast speed of about 5,000 kilometers per second, and the only driver that could cause it to move at this kind of a velocity was this massive black hole which is sitting at the center, at the galactic center. Uh, Now nature produces a variety of black holes, and you have supermassive black holes at the center of galaxies, which could be 1,000,000 times or 1,000,000,000 times the mass of the sun. There are even what are called intermediate mass black holes, which have about a mass of about 1,000 times the mass of the sun. There are stellar mass black holes, which have a mass of about 10 times the mass of the sun, and there are micro black holes. But with black holes, we know that the biggest problem is about detection, right? Because again, like we spoke about dark matter yesterday, you do not get the luminosity from it, you get just the gravitational effect, and that's exactly what you have to do if you want to study it, right? And that's what we'll be doing today too. So now what happens if you have an active galaxy? You have the black hole sitting at the center, you have an accretion disk, there is a broad line region and a narrow line region. So obviously these objects, the stars or whatever objects you have in this region, they are moving at very fast velocities because of the presence of the black hole, and they basically give you broad spectral lines, which we'll just talk about. So now over here you can see this is a beautiful image of stacked up. These are stacked up spectra of 326,886 Sloan. We spoke about SDSS spectra. So these are SDSS spectra using what is called the BOSS survey. This was a survey basically of quasars where they observed them for this large number. And what's very interesting in this plot is that these are all stacked up, right? And you can see that redshift is increasing as you're going on the y-axis. So if you have, supposing a spectral line over here at 0 redshift, you can see that the same spectral line is getting shifted to a longer wavelength, right? That's what's called redshift, and therefore this same spectral line with the streak which you see is basically moving because the same spectral line which was at this, say at 4,000 angstroms, when it is at 1, it has moved at a redshift of 1, it has moved to a longer wavelength here. When it's at a redshift of 2, it moves with a further longer wavelength, and 3 further, and in this way you can see that the wavelength of the same spectral line, say which was at 4,000 angstroms, moves to another point as this redshift changes, right? So here we had it at redshift 0 and here we have it at redshift 3. So that's what you can see in this, the way these things are moving. Now this does not exactly, you can see it's not exactly monotonously increasing. We are going to use a formula where we'll say that the redshift is increasing as redshift observed multiplied by 1 plus z, where z is the redshift of the object. But in reality, when you actually use cosmological calculators and models where you have a certain amount of space-time curvature, then you do not have exactly a linear shift of that way. There's a slightly difference in the shift, right? We'll talk about that a little bit later in more detail. So AGN, active galactic nuclei, there are a whole variety of active galactic nuclei which are observed because you have synchrotron radiation coming from this, and therefore these are very good they are radio loud sources. So a lot of the AGN work used to be done in radio. It's also observed very well in X-ray, and there's a lot of work being done like that. But if you actually see, the AGNs are basically of two types. There's the radio quiet and there's the radio loud. In the radio quiet ones, we have these ones which are observed in optical, which are Seyfert galaxies, and QSOs are quasi-stellar objects or quasars. Seyferts are further classified into two kinds, which are called the broad lines and the narrow lines, depending on their spectra, right? The radio loud ones, you can have blazars, and they are actually classified into FR1, FR2. There are different categories based on essentially the spectrum of which you're getting from the AGN. And that's why today we are going to talk about the spectrum of AGN, because we already had a session on photometry. I wanted to do something which actually touches a little bit upon spectroscopy, so that you can get a feel about what are the kind of things that people do when they, when they do spectroscopy. So I'll just brush through a little bit of spectroscopy. What is spectroscopy? That basically if you have a light source, right, say a white light source, and you pass it through a prism, what happens is that the dispersion is wavelength dependent, right? Depending upon the wavelength, you will have different amounts of dispersion, and therefore you will have, you actually see the spectrum or the rainbow, because the angle of dispersion is different for different colors. So when I have the source of light, I have it like this. So over here the first one is the case of a hot bulb. So a hot bulb is a set where you're actually you have a hot, it's going to emit by Kirchhoffs laws. So as per Kirchhoffs laws, if you have a hot bulb, right, it is a hot dense gas, and this dense gas will actually give you what is called a continuous spectrum. So by continuous spectrum you mean that it will give you photons in a variety of wavelengths ranging from 0 to infinity in principle, with a difference in intensity in different wavelengths. And like you all know, Wien's displacement law, depending upon the temperature of the source, the temperature of the bulb, the peak of this spectrum will shift, it will vary, right? And it will be at shorter wavelengths if the source is hot, and it will be at longer wavelengths if the source is cold, right? And in that way you will have a different continuum spectrum coming from this hot dense gas, which is this. So that's the continuum spectrum. Like I said, it will range from 0 to infinity, only the intensity will vary depending upon the temperature of the source. So this is a Planck backbody radiation curve, and the peak of it will follow Wien's displacement law, where you will have the peak depending upon the temperature of the source, right? The next one over here, which you can see over here, is that supposing if I have a heated gas, if I have supposing heated hydrogen gas, which is thin, which has low density, right? This is low density heated hydrogen gas. We need it to be low density because that would reduce the amount of collisions. And then in that case, overlaid on this continuous spectrum, you would even get what are called emission lines. That means supposing if this is hydrogen, you will get specifically lines coming at particular wavelengths which are determined by the hydrogen component of this. So you will have these different things and emission lines depending upon the chemistry of this gas, which is hot. Now the third option is if you have a cold gas, again it should be a thin gas, low density gas. Then in that case, the cold gas is the hot air, the hot radiation will pass through the cold gas, and since the gas is cold, the electrons in the cold gas are going to absorb certain characteristic wavelengths and give you what is called an absorption spectrum. Now emission and absorption spectrum are very important because these are characteristic wavelengths depending upon the chemistry of this gas, right? So depending on whether it's hydrogen or calcium or whatever is there in the gas, you will get the corresponding emission or absorption lines, right? And based on that you will get the spectrum. And these are very important things because the continuum spectrum is an estimate of the temperature of the gas, but the emission spectrum and the absorption spectrum are indicators of the chemistry of the gas as well as the physical conditions in which you are getting these emissions, right? So in astronomy, we do all spectroscopy is done in angstroms, where angstrom is the unit of wavelength, where 1 angstrom is 10 power minus 10 meters or 10 power minus 8 centimeters. And the characteristic hydrogen lines, the H alpha line, it's a redder line, it is at 6565 angstroms. Hydrogen beta or the Balmer line is at 4863 angstroms, and you have various lines of hydrogen. These are the Balmer lines. You also have in astronomy what are called narrow forbidden lines. Now forbidden lines these are forbidden lines because they are forbidden by the first by the first approximation in quantum mechanics for lines, spectral lines. But in the case of astronomy, where you have this low density gas, where you have a minimum of collisions, you have very low collisions, you also have these forbidden lines. Now forbidden lines are not generally observed in the lab or on the earth, because for this you need to have gas which is of very low density. So it would be the best of vacuums that you could ever have that would give you these kind of forbidden lines. So these are only seen in astronomy. We do not see this in our general labs. Okay, so YB has a question about Kirchhoffs laws. So one second, why is it Kirchhoffs laws illustrated? So yeah, so Kirchhoffs laws, there are in electricity also, you do it in network, this thing, but Kirchhoffs laws are laws which actually tell you about the emission or the heat emission which you are going to get from sources, from hot sources. What is the kind of heat emission you get from sources, right? Okay. Now let us look at stellar spectra, because So what you see is hot stars are O-type stars, G-type stars are cooler stars. So you can see in very hot stars, you do not have too many spectral lines. These are the helium lines marked, the hydrogen lines are there. As you go to colder and colder stars, for example in G-type stars, you will see the potassium line, magnesium line, the sodium line, and then you go for still colder stars, you see the calcium line, etc. And these are the various spectral lines which are there in stellar spectra. Okay. If you look at planetary nebulae, you will get another set of lines. In planetary nebulae, these are very diffuse medium, and therefore this is the hydrogen alpha, H beta, H gamma, H delta lines. But along with this, you also have the forbidden lines, which is the oxygen. In astronomy, for example, if you say nitrogen 2, this is doubly ionized, this is singly ionized. So for example, H2 means hydrogen without the single electron it has, and that's why it's called H2. This is also with lost this thing. So if you have a forbidden line, we put these square brackets, and that's the indicator of forbidden lines. In active galaxies, like I said, this is the composite spectrum which is got from SDSS of a whole set of active galaxies. You can see that there are a whole set of spectral lines we get. Today we are going to concentrate on this H beta line. There's an oxygen line right next to it, which is this, which is a small bump. But we are going to talk about the H beta line because you can see that this line comes within the optical part of the spectrum, and we are going to see what can we do using specifically this H beta line, right? But in principle, you have a whole set of lines. These would be in the ultraviolet, you would need to observe in the ultraviolet, while these would be in longer wavelengths, and further ones would be in the infrared wavelengths. So if we take a close-up of this view, this is this part, we are looking at this part. You can see over here, this is my H beta line, and we have various other lines next to it. This is helium, this is iron, there are various other. This is the H alpha line, beta, this is gamma, delta, and okay. So another important thing in quasar spectra is you have what are called broad lines and narrow lines. Now why are lines broad? Lines become broad because supposing if you have a star going around, for example, the AGN, the supermassive black hole, there is going to be a Doppler broadening, right? We'll talk about that in a minute, where part of it will get redshifted, part of it will get blue shifted, due to which it gets broadened. And this broadening is obviously, since it's happening because of the velocity, we can use it to find the velocity of those stars or those objects. So here you see, like I said, that's again our active galactic nuclei. We are going to look at objects which are in this broad line region. These are objects which are outside the accretion disk, and they are going to give you these broad spectral lines. So what happens is, if you have a black hole, let's say this is the observer, you are looking at the black hole, at a galaxy which has a black hole, and let's say you have these clouds going around the black hole. Now you will have a set of them which are coming towards you, so they are going to get blue shifted, and there's a set of it which is going away from you. This is going to be red shifted, right? And that's why the spectral line, which should have been at a particular wavelength, it gets broadened. So okay, so these are your broad line clouds, and you can see that this is happening. So therefore I have this thing moving with these velocities. This is my emission which is coming from there. This gets blue shifted and this gets red shifted. So by blue shifted, what did you mean? That the wavelength of it gets reduced, right? It gets reduced wavelength, while what is red shifted, it gets stretched. There's red wavelength, okay? And if you just use simple school, if you use simple school physics, which we've learned, that the force on this object is going to be ma, and what is that? That is the gravitational force which it feels because of the black hole. So what is that? That is gmm by r squared, right? Gmm by r squared is a minus force because it's an attractive force between this mass and the mass of the black hole, and that is nothing but equal to mv squared by r. It's small m into v squared by r, right? So the small m's get cancelled. Oh, here I should have written a small m, and therefore you can get the capital M, which has become r into v squared divided by g, right? So if I want to get the mass of the black hole, that's just going to be r. I need to know this distance, I need to know v squared, and I need to know g, and I can find out this, this mass, right? So the other factor is we are going to add another factor which is called F, which will be the virial ratio. I'll just talk about it. So in short, what we said is that if you have a small mass m moving in a circular orbit of radius around a larger object of mass capital M, your gmm by r squared is equal to mv squared by r. Sorry, the m is gone over here, and therefore you can get the mass. And that's exactly what we are going to do, that the mass of the black hole, we have something called a virial factor which will tell us about because of the distribution of clouds, we take a factor of 3/4, but if you take it as 1 also, your error won't be large. Next, what you need here is you need the radius of the broad line region, which is over here, which is given by this formula. We won't get into deriving it, just trust me that this is the formula for the radius of this broad line region, multiplied by v squared, right, which is the velocity of that, and divided by g. G is the gravitational constant. Now, how do we find the value of v? The velocity is found basically from the spectral lines. So here we look at the spectral line. So let's say this is the H beta line. Now the H beta line, if you remember, I showed it to you, that part of it is going to be blue shifted and part of it is going to be red shifted. So it gets broadened because of the velocity. Okay. Now for spectral lines, we define something called an FWHM, which is the full width at half maximum. So let's say we can approximate the spectral line like a Gaussian, right? Let's say our spectral line is a Gaussian. So if this is the brightness F max, I take half the brightness, which is F max divided by 2, and I take this width, right? I take this width, and this width is what I call the full width at half maximum, right? That is how much of this region is the width at half the value of the maximum. And now this full width at half maximum is going to actually, this is the delta lambda, right? These, if you remember, this x-axis is basically wavelength, lambda. This is intensity. So you have a broad thing like this, and this delta x is going to be nothing but a delta lambda, right? Now we are going to use our formula for Gaussian fits, which is V by C is equal to delta lambda by lambda. And that's how we can find out the velocity of this thing, right? So that is what we are going to do. That's the aim of our exercise today, to find out the mass of the black hole, for which we need to find two things. One thing is we need to find out the radius of the broad line region, and we need to find out the velocities, right? And that's what we are going to do now. So let us now, we want to download a spectrum. How would we download a spectrum, right? So I'm going to share my screen, and let's look at my browser. Yeah, let's take my browser, and what we want to do is we basically want to download the data. Now if you remember, we have already seen this before, NED Astronomy, right? NED Astronomy, that's a website which is called the NASA Extragalactic Database. So this basically has data for objects outside our galaxy, essentially. Some objects are there from our galaxy, but they're essentially meant for objects outside our galaxy. So I can click on this, right? And now what I'm going to try to do is I'm going to download the spectrum of an object, right? Of a quasar or this thing. So we are going to download the spectrum of an object which is 3C273. This is one of the earliest known, brightest known quasars. It's a very well studied quasar, and it's a very bright quasar, very well known one. And we are going to basically study this one, okay? So let us say go, and we are going to look for the data which the NED database has on this object, 3C273, right? Okay. So I hope everybody is with me and you've gone into NED and you're looking for this. I'm going to wait for a minute for comments on the chat. Please tell me if you have not, but everybody go on to NED. And yeah, if there's a problem, please mention it on the chat window. I've got the chat window open. But otherwise, please go to the NET database, do NET astronomy and write down the name of the object, 3C273. Okay? Please do that, and if there's a problem, you mention it on the chat window. Okay? So then I think nobody's written anything, so let's press go. So now the NED is basically going to tell me what is the data it has about this object. What is happening? Okay, I'm just going to reload and just see. So 3C273, we say go. I don't understand why nothing is coming over here. No problem, I have a backup. So here you can see my screen. I have pressed 273, press go, right? And now what happens is it lists for me various set of objects which it's going to actually, for which it's going to, all the data which it has for 3C273, right? So I'll go back to my thing over here and oh, I think it's done it. No, it's not done it. Okay. Yeah. So please see. Okay. 3, 7. Okay, you wrote 3 instead of 2. What was it I doing? 3C273, right? Ah, okay, sorry, I've written 273. Ah, so probably this object doesn't exist. Thank you, Femida. Probably that's the mistake I did. But I still don't have anything coming. I hope all of you all have something. 2733 is not working either. 3C, one second, I just 3C273. Okay, well, let me check if I need to keep a gap. Okay, Femida got results. 3C273. I don't know why this thing is just not working. Though my net is working fine. I don't know what is it. So we can look over here. See, you see 3C273. Yeah. So 3C273 is a quasar located in the constellation Virgo, and it was one of the earliest discoveries in AGN science where people actually found this thing, and you can see that it is 3C273. Okay. Now I'll go back to my thing and I'll wonder why am I not getting an output. 3C273. This is strange. Yeah, everybody seems to be getting results. I don't know why I am not getting it. Okay, so I don't understand. I checked it earlier. Oh, yeah. Thank God. Thank God for that. Yeah. Oh, it's gone. So now in the results, what it's going to show you, it's going to show you all that it has found for this object. It almost did it and then it... I don't know why my thing is not working. Can somebody share their screen where they have got their objects? Just see, do you have permission to share? Yeah, no, the share, I'll show you the data in the chat, don't worry. So I can show that to you. So what you'll basically get over here, this is what you will see. You can see this, right? This is what you're going to see. You're going to see this list. Now click on Spectra, okay? Click on Spectra, okay? And once you click on Spectra, you'll see a whole list of spectra available, which are available for this object.
Priya, can you
yeah,
hear?
Mamta, can you run it for yourself? I don't know why I'm not getting it.
Yeah, we can see your screen, and that is actually.
It's WhatsApp.
It's your WhatsApp.
WhatsApp is coming on, ma'am, yours.
Okay, but now can you see this?
Now it's fine.
Now we can see your screen.
Yeah, but strangely, my problem is that it's not giving me the output, right? Mamta, can you run NED and get this 3C273?
This will stop screen sharing.
Yeah, it works fine. I don't know why. Or if anybody else can share their screen.
I can share it.
Just run a NED search on 3C273. I'll stop my share. Yeah, no, I was trying to check on WhatsApp whether everything is fine or not. I don't know why is that NED thing not working, right?
Okay, I think I can't share my screen. The reason, oh, sorry. Okay, yeah, maybe now I can share it for Saskia.
It almost showed that output and then it stopped. I don't know why.
Right, so there we are. Can you see my screen?
Yeah, okay, so Mamta, just scroll down. I'll just talk a little bit and then they can download it from here. So if you scroll down, you can see that there is data here available for this object, right? And like as she's scrolling down, did you click on Spectra? Just go up, go up, and here just click on Spectra. Yeah, click on Spectra. So this is specifically the Spectra which is available for 3C273. Right, so now you can see the first one, just go slowly, Mamta. So the first one, you can see that this is a spectral line which is in the Lyman alpha forest. So this is typically in the ultraviolet, right? You can see it's at about 1153 angstroms, right? So we'll scroll down. We want to look at the optical line. We basically want to look at that Balmer line, right? We want to look at the hydrogen Balmer line, and therefore let's just scroll down. Just scroll down, and you see the next one. You can see is an optical one, which is 3984, 57. We'll go further down. Just go further down. Yeah. And now you can see, let's just stop, Mamta, sorry. So you can see over here that this is the H beta line. We basically wanted a spectrum of the H beta line, right? You see, which is ranging from 4000 to 8000 angstroms, which has a resolution of 8.5 angstroms. And we want to download this spectrum. So please click on the VO table. Mamta, get it on the VO table. Yeah, and click on that and you will be able to download the spectrum in VO table format, right? So just go back and do it. Maybe you can click it and, yeah. So you're going to click on the VO table part and you're going to download the spectrum, right? So you download the spectrum in VO table format. Yeah. Yeah, scroll, yeah, this one, 8.5, yeah. And I don't know whether save link, oh yeah, VO table, yeah. So say save, and please share this in the directory which is the one you know, save, and yeah. And that's it, that's all we need from net, so you don't need to worry about, Mamta, thanks so much. We don't need that anymore. Now we have our spectrum, right?
Yes.
Yeah.
So shall I send it?
Yeah, Samantha, you can stop sharing.
Stop.
I hope everybody has downloaded this file, right? I will again share how and where you get it from. I hope you all can see. You can see my screen, right? So you come to NED. On NED, you will write 3C273, Then you press on go. Then you'll get this screen. Click on Spectra, okay, for Spectra. And then find the spectrum which is there for H beta line, right? Find the spectrum for H beta line and download in VO table format, right? So I hope everybody has done that. Download that in VO table format. Once you have done that, we will open TopCat, my favorite once again. We will open TopCat. You will say File, Load Table, and you are going to load the data file which you just now downloaded, right? So you will say File Browser. We are in Day5. I have already downloaded the file and downloaded the file, and I think it's up there. Yeah, this is the file. Only be careful that in table format over here write VO table, okay? Write VO table and say OK. I hope everybody is with me. You've downloaded the spectrum, then open TopCat, say load file, write the table format to be VO table format and take this file and say OK. I hope everybody's managed that, or write it in chat. If you want, you can't see my TopCat screen. Okay, I'll just stop share and I'll share again. I hope you all can see my TopCat screen now. I'll just repeat what I did. I opened TopCat, right? This is TopCat over here. Then I press on File, I say Load Table. I go to my browser. This is the file that you just downloaded, right? So you select this file and change your table format to VO table, okay? And then say OK. So now you have the file in VO table format. I hope everybody has managed this. In case you have a problem, I'm looking for comments on the chat section. If you can tell me that, you please tell me that. And I'll give you all a minute to open that and just see. Yeah, please check that you all have all managed to get that. If you had a problem with this, I'll share the file in the chat window and give it to you. So in case people have had a problem in getting the file, I'm sharing it on the chat. You can download it. This is a VO table format file, so you cannot read it with a normal reader. You will have to use TopCat to read it, okay? You can't read it with a text reader, you'll have to read it with TopCat. Very good. So I hope everybody's loaded the table in TopCat. I'll give you all another minute or two to do that. I'll just be there. 1 minute. Hello, yeah, I'm sorry. Yeah, so I hope everybody loaded the table in TopCat. Very good. And I hope you can see my screen. So now let's look at our table in TopCat. I hope you can see what I'm showing you. I hope you all can see my TopCat screen, right? Yeah. Yes, thank you. Thanks, Urvashi. So you see that in this data, the data is frequency with flux. So generally in astronomy, we work more with wavelength, and that's why we are going to convert our frequency to wavelength. So what you're going to do is this column part, right click on new synthetic column, okay, new synthetic column, and here we will write wavelength, okay. Now many of you all would know how do I calculate the wavelength. the wavelength is going to be my c, that is the velocity of light, divided by the frequency, right? So here I am going to write 3 into, I want 10 power 8. So in TopCat for 10 power 8 there is a function called pow. Okay, so pow I will say 10 comma 8. This basically means 10 power 8. So this is c, right? C is 3 into pow 10 power 8 divided by the frequency, right? So I am trying to find out the wavelength, right, by taking the formula that wavelength is equal to c, which is the velocity of light, divided by frequency, right? So I will say okay. And here you see this is my wavelength. Now you can see this is into 10 power minus 7 meters. I want to convert this to angstroms, and therefore to convert it to angstroms I will click on replace column, right? And you know that 1 angstrom is 10 power minus 10 meters, right? And therefore if I want to convert this to angstroms I have to basically multiply it by 10 power 10, right? So now I can say multiply 3 into pow, again I can use the function pow, and I'll do 10 power 10, right? So I am basically, this wavelength which you can see over here, this is in units of meters, I am converting it to angstroms. So I say 3 into 10 power 10 and I say okay. So now you see this is my wavelength in angstroms, right? I hope everybody can see the screen well. This is my wavelength in angstroms. Now the next important thing which I need to do is, we need to do something, 2 things important. We need to, if you remember yesterday, we used Ned-Wright cosmology calculator. Again, I have got to use this to find out the distance to the source, right? How will I find out the distance to the source? So I am going to open Chrome, right? And I am going to go back. I need to find out, okay, we can look at this, or I can tell you in advance that 3C 273, we want to know its redshift. So what is the redshift? I'll just find it out. 3C 273, the redshift over here is 0.158. So please note that the redshift of 3C 273 is 0.158. Now we are going to use the same yesterday what we used, the Ned-Wright cosmology calculator, to get the distance. So you know that in principle if you take c by z you can get the distance, but because of cosmology we have to use the Ned-Wright cosmology calculator. Click on this, right, and here I will write my value of z, which is equal to 0.158, right. So I am going to use this to calculate the luminosity distance of this object. So I have 0.158, click on general, right, and if I click on general you can see I get the distance over here, and my distance is given over here 760.5 megaparsecs, right. So please note this as the distance. This is the distance to our source, 760.5 megaparsec, okay, 760.5 megaparsec, okay. Please take this as the luminosity distance. Okay. I hope everybody is clear with this. Should I repeat something? This was done yesterday by us also when we did the stuff on dark matter. Like I said, in cosmology when you are measuring distances, it involves a lot of general relativity and complicated calculations, and therefore for people like me who do not do cosmology, for us this cosmology calculator is a far better option, where we can very comfortably calculate distances without having to worry about the complicated cosmological formulae, right. So this cosmology calculator basically does the work of doing that, and right. So I hope everybody can see this 760 megaparsecs, right. In the chat please let me know if anybody is having a problem. Okay. Now the next thing which I have to do, which I am going to show you, is the next important thing, that we were just talking about cosmology and the effects of cosmology, and that basically tells us that the wavelength that we are observing, this wavelength has obviously got shifted, right? We know that this wavelength has got shifted. Why? Because of the redshift, right? So how does it got shifted? The observed wavelength is basically 1 plus z into the lambda of the source, right? So the original wavelength which was there at the source is different. What we are observing is something different, right? And therefore, what we are observing is actually this thing, and therefore the source wavelength is actually what we are observing divided by 1 plus z. So all the wavelengths which you remember in that TopCat table which I showed you, the wavelengths, we have to convert them to rest frame wavelengths, right? We have to convert that to rest frame wavelengths, and with that we can get the wavelengths of our of this for the spectrum. So I am going to do that. I hope you can see my screen. You can see my screen? Yeah, I'll just see in the chat. Okay, so Femida wants the power function. The power function, supposing if I want 10 power 8, I will say power 10 comma 8. This is 10 power 8. Okay, so the power function is power a comma b, where a to the power of b is the resultant, right? So I hope you can see my TopCat screen, and I hope you'll remember how I did power. Should I repeat that? Should I repeat that thing, Femida, or it's fine? Thank you. Okay. So now the thing is, we need to make a new column. I'm going to say new synthetic column. And what is the synthetic column? It's going to be wavelength of the source, right?
And then we can see your AGN spectra screen, your TopCat screen.
Okay. I hope you can see my screen now. Please let me know. Yeah, you can see. Okay, thank you. So see, so what I was showing you before this, I told you that because this source is at a certain redshift, right, 0.158. Therefore, the wavelengths which we are observing are not the actual wavelengths of the source, right? So we saw that, if you remember, I showed you that formula which said that observed wavelength is equal to 1 plus z into source wavelength. But now I want to find out my source wavelength. So I will right click over here, where I say new synthetic column, and I will say wavelength, and this is source, or I can say, okay, let's say source, and my expression will be this same wavelength which I already had. I have to divide it by 1 plus redshift. So that means 1 point, and we know the redshift is 158, right? So what am I doing? To get the source wavelength, I am using this wavelength and dividing it by 1 plus z, right? Where z is equal to 0.158, right? I hope you can see my screen. Can you not see my screen? I'll stop share and share it again. On this, I hope you all can see my screen. Yeah, you're able to see. Very good. So what you have to do is what I was showing you over here. This. You right click on this. Yeah, you right click on this. If you right click, you will see new synthetic column, right? And for a new synthetic column, we'll call this column wavelength of the source, right? And I'm going to say it is this wavelength which we have divided by 1 plus 1.158. How did I get 1.158? This is 1 plus z, and z is equal to 0.158. So I'm just doing it like that, right? So this is my wavelength. So this is now my source wavelength, which is what we call the rest frame wavelength, right? This is the rest frame wavelength, because otherwise the problem was that because this source is at a redshift of 0.158, therefore the spectral lines had got shifted, redshifted. So instead what I have done is I have done this, right? So I am going to say okay. I hope everybody is with me and all's fine. Yeah, so I will take this and I will say okay. So here you see I have a new column which is the wavelength of the source, right? And that wavelength of the source is given by this thing, right? if we plot it, I can show it to you. You can see this plane plot, right? If I were to plot wavelength versus flux, okay, this is what I observed. Now what I've done is I've corrected this and I've got a new value, and now what I have is I have wavelength, and here now this is wavelength of the source, sorry, this is wavelength of the source versus the flux, right? So now you see we have two different lines. I can join them with lines. Right, so what you can see in this is, originally, I can show you once again, originally we had this was our data, which is the wavelength which we observed, but we know that this is a redshifted wavelength, right? It is redshifted because this object has some redshift, right? And therefore what I did was I divided by 1 plus z, so then I got the actual. Now I get the rest frame wavelength, which is shown over here. So the blue wavelength is the real rest frame wavelength, right? While the red one was the wavelength which I had when I observed it, right? So this is this, right? Another important thing, so that is, you can see this in action. Another important thing is that we also can and should convert the Balmer line. I hope you can see my PPT. Just tell me in the chat if you can or you can't. Can somebody just talk and tell me, can you see my PPT? Can you see my PPT?
Yes, ma'am.
Okay, very good. Thank you. So we also have to remember that this is the Balmer line we are talking about, and the Balmer line has got shifted. 1 plus z is this 5631. So if we are looking at observed wavelengths, the Balmer line is, you can't see?
No, we can't.
Oh.
Now we can't.
Okay, 1 minute, no problem. Oh, it's somehow stopped share. I don't know why it does that.
Now we can see it.
Okay, now you can see. Okay, very good. So this is, I was just talking about the conversion which we've done for wavelength, right? And I hope this is clear to everybody that the observed wavelength is actually 1 plus z times the source wavelength. And therefore what we did in TopCat is we calculated the source wavelength by doing the observed divided by 1 plus z. And my z is 0.158. So therefore I did observed divided by 1.158. I hope everybody managed this, right? This is all done by everyone. Yeah. You've got the rest frame wavelength. Now the other thing on the y-axis we had is flux, right? Flux or flux density. Now the flux density also, we will not go into details about the flux density, but because of cosmology or redshift, you are also going to have a change in the flux density, okay? And this flux density is basically there's going to be a difference in the time because there's time dilation. There's going to be a difference in the energy because the energy is shifted towards longer wavelengths. There's going to be a difference in the bandwidth. So cumulatively, the effect of the flux becomes the observed one is the source divided by this. So now if we want the source flux, we will have to multiply the observed flux into 1 plus z. So that's what I'm going to do. I'm going to say stop share and I'm going to go back to TopCat. And I hope you all can see my TopCat, right? Everybody, yeah, say yes. Can you see my TopCat? I hope you all can see TopCat. Yeah, very good. So now we have made, see, we made this change to wavelength. Now we need to make the change to flux. But wavelength we divided by 1 plus z. Flux we will have to multiply it by 1 by z. So here at near close to flux, right click using your mouse or whatever, and you say new synthetic column, and now I'm going to say flux source, right? So I want the flux of the source, and I will say flux, right? My column is called flux, and I'm going to multiply this now into 1 plus z. So I don't need a bracket also, I can put 1.158. So what am I doing? I am multiplying the flux into 1 plus z, right? And the z for this source is 0.158, right? So I am multiplying this and getting the flux of the source. Okay, I hope everybody is with me. I'm just stopping, pausing. Let me know if you're all doing this thing. So first thing we did is we converted wavelength to source, rest frame wavelength, and the second stage is we are changing the flux to source flux, right? Because of the relativistic effects of the redshift, we corrected that. So I hope everybody's done this, and can I press on OK? Yeah, somebody tell me, is it fine? Can I press on OK? Yeah, Mary, yes, Urvashi, okay. So I press on OK. So now I have my two important columns, which are wavelength of the source and flux of the source, right? I needed this because this was the factor which would actually, define what is it for the source in rest frame, right? I have to convert everything to rest frame, and therefore I will do this like that, okay? Now I will plot this again. Here is my plot, and I am going to remove this. So I'll just have a single plot. Okay. This is my plot, and now on my x-axis, I am going to, Now I am going to plot on my x-axis wavelength of the source. Okay. You have to take the redshifted corrected wavelength. So wavelength of the source will be on x-axis. And the y-axis, like you guessed correctly, will be flux of the source. Don't take the old flux, okay? Please take the new flux. So now this wavelength and flux is corrected for redshifts, right? So I have wavelength of the source and flux of the source, right? So I hope everybody's done that, and you can see your plot over here. This is your graph, right? So Urvashi, yes, you managed. What about Mary, Shankha? Mutasir, did you get it? Yes. Did everybody get this plot? Yeah, please everybody look if you got this plot. Please look for the plot. Yeah, I see 3 new messages. Yes, Rahul. Okay, Ishan, you got it. Shankha, very good. So this is the final spectrum which I have, which is redshift corrected. Now the hydrogen beta line is this line. Okay, this is the hydrogen beta line, H beta line, right? So now what I'm going to do is I am going to only mark, please use TopCat, right? And on TopCat, click subsets. I'm only going to pick up the spectrum which belongs to H beta, okay? I don't want the other lines. They are not of my interest. I only want the H beta line, which is this line. This is the H beta line. I just want this one. And for this, I've got to find out the full width at half maximum, right? So I am going to click on subsets. I will say draw blob subset, and I will mark this part. Okay, mark it. Again, click on subset, finish drawing bulb, and call this HB. This is your hydrogen Balmer line. Okay. So I can remove the rest. I only want this line. Okay. I hope everybody's managed this. I can see there's a question, Urvashi, how to get 2 graphs simultaneously on the plane plot? Oh, very simple. 2 graphs simultaneously on the plane plot is if you, for example, you just add this. You can just add this. You just say this and you add, and here you say which table do you want, and here I can say, see, I'm going to take wavelength versus flux. So here I can put the whole thing. So if you look over here, you can see the observed thing was this green one, right? And when I corrected it for redshifting, I got the red one. So I'll actually change it. This one is the one, okay, this is for source, correct. And this one is, this green one is, this is the one which I observed, and then because of the redshift I had to, this thing, so it became a shorter wavelength. So the real source thing is the red. This was the original data. Now it is this, and this is a hydrogen beta line, okay. So now I'll go back to this, and this is my thing, and I will only look at my H beta line, which is in pink over here. So I just look at my H beta line, and if you have a mouse you can use that to zoom and look at the line more closely, right. TopCat also gives you the option of, if you do access, you can click on grid and you can say draw grid, okay. You can say draw grid. You can reduce this thing of the grid also. Okay, more detailed. Right, I've made a grid like this. I can also go into access and say range, and here I can change my range 4600 to 5000. Okay, so this is my line. This is my hydrogen beta line, and I can change the Y and get it like this. Okay, so I hope you all managed this. Please see if you could manage it or no. If you can't, I will repeat it. I'll just repeat it once again. Let me close this. Let me go from the very beginning. This is my TopCat thing. I'm going to plot, click the plane plotting window. I'm going to plot wavelength of the source in x-axis, and y-axis is flux of the source, this, right. I know this is my hydrogen beta line, so I'm going to click on subsets. I'm going to say draw blub subset, and I will mark this over here. I click again on subset and I call this HB, right. I can call this HB2, okay. This is my HB, okay. Now what I do is I click on subsets and I remove all. I only look at HB2, this, okay. Now what I want to do is I want to zoom on this so that I can find the FWHM, right. Please let me know in the chat, can you all see my video and all properly, right? Everything is good? Yeah. Okay. So now I want to see this in more detail. So what will I do? I can click on axis. I can make the range. Let me make the range. We had done 4600 to 5000. This, and I can even change my y-axis. I can even give values if I want, or I can just pull this and do it like this, right. So both things are possible. Similarly, I can reduce this and do this, and if I want, I can also change the form and add a line, make this a line. So this is my spectral line. I'll try to make my spectral line a little wider. Okay. So is this clear to everybody? Can everybody see the spectral line good? Yeah. Now I'm going to click on axis and I will click on grid. So I can say draw grid, click on this and you can get a grid. Okay. I hope this is clear to everybody. I'm just pausing for everybody. Just see if you managed to get this thing. We are inspecting the hydrogen Balmer line from the AGN, right, to find out the full width at half maximum as well as the brightness at continuum. I'll show you what is what. Okay.
Ma'am, how did you connect the dots?
Yeah, so if to connect the dots in TopCat, there is something called form. There is, if you have this plot, you click on this and you know, if you put on positions, you can see there's something called form. In form, you have a set of options. Either you can put the points, if you want to put the marked points, you can put the marked points like this, right? If you want, you can add, you can make the size bigger or smaller. You can also add line, which is add line this. You can also do this thing where you can add a linear fit, but this is not a linear fit, so linear fit is bad. You can add this actually that does fitting. This also does Gaussian fitting actually, but it does various things. So here you can choose. I hope Shankar you managed.
Yes, ma'am. Thank you.
Yeah, thanks. Yeah. So I am removing this mark so that we can look at our thing better. And I am just making it a little thicker. You can adjust the thickness using thickness. There. Okay, 1 minute. It's not online. Yeah, okay. So now it's online and this. So this is fine. Is this fine, everybody? I hope this is fine for everyone. Yeah. So I wanted to have the full width at half maximum, right? So this is my maximum, right? This is my, I can consider this to be my this thing. So I want to get this full width at half maximum. For that, ideally speaking, then I can rescale because I want to know where is my max and where's my half max. So I can actually go back to position. I can say plot and I can say rescale. So this is my rescaling, and if I want the half maximum, I can, let's say this is the maximum. If I take half the value of this, it would be, look at this point versus this point. So this is what I'm going to call my full width at half maximum, this. Obviously there are errors in this. Ideally speaking, when you were doing this, you will have to actually write proper Python code to get these points. You'll have to do a Gaussian fit to it, and you will have to find out this full width at half maximum. Just now we are doing it in a rough way, but basically the purpose of this exercise is to show you how to do these things, right? In perfection it can be done differently, because obviously you cannot finish work for a paper in 1.5 hours, right, or in 2 hours. It takes much more time. But the purpose of these tutorials is basically to give you a flavor of how do things get done, right? So now let me start with this. So here you can see down, over here down where position is, you can see the coordinate. You see this is 4840, right, 4840, and this point, this is 4840, and this point over here is 4900, right? So this difference over here is about 60 angstroms, right, 60 angstroms. So this is my delta lambda, okay, this is my delta lambda. So my the delta lambda, which I am going to use to find out velocity, right, v by c is equal to delta lambda by lambda, and therefore delta lambda, v is equal to delta lambda multiplied by, we have what, delta lambda by lambda is equal to v by c, and therefore v is equal to c into delta lambda by lambda, right? That's what I am going to do. And so I am going to take my delta lambda, here I have got it as 100, and let's proceed with that. The other thing is we need to know the continuum brightness. The continuum brightness is given by, we actually see this is the continuum, it's coming somewhere between this and this, right? And therefore I get this value somewhere over here, and this will be the, you see this line is overlaid over the continuum. So the continuum is somewhere over here, right? Let me show you the whole thing. You see this is the whole plot. So I have the whole continuum, and over that I have these lines. So I want to actually use this to assess what is the value of this continuum. So I am going to take that part and look at this, right? So this is the point at which you are having the Balmer line. This is the approximate value of the continuum, and this will be the value of the continuum at the value of the Balmer line, or 5100 angstroms. I am going to look at it over here. So where we have 5100, I can approximately say that will give me my level of the continuum, 5100. That's where the line is gone. So I can now adjust it and get it over here. So I hope you can see the numbers down there, right? And you can see that this is 2.8 into 10 power minus 29, okay? 2.8 into 10 power minus 29. Now I will show you how do we use these two numbers. So the two numbers we have is 100 angstroms and 2.8 2.8 into 10 power minus 29. Okay, so that's it. With that we finish with TopCat, and we'll get back to this. So I hope you can see my screen. Please tell me, I hope you can see my screen in the chat or audio. Please tell me. Can you see my screen?
Yes, ma'am.
Yes, okay, very good. So we already did this correction for flux density, and now we are coming over here. If you remember, this is our FWHM. Here what we do, if we, you can multiply it for yourself. See, this is the continuum where, what this, we said this was our FWHM, and this is the continuum, right? So this is the continuum at this value. This will be that. The FWHM will be a line parallel to this, and you get this width, right? So we actually took 100 when we took it straight, but actually if you take it like this, you'll get a little bit more. You'll get 120 or 30, this value, right? So velocity is what? C into delta lambda by lambda, right? So C into 100 or 140, whatever you get, divided by lambda. Lambda, this is the wavelength of the Balmer line in rest frame, which is 4863. So if you take this 150 value, I think you get a value of 6.6 into 10 power 6 meters per second. So this is telling you that this source is moving at a velocity of 6 million kilometers, right? 6.6 into 10 power 6. This is what we are going to use in our formula, right? So this is, so FWHM basically has given me velocity. Now the next thing I want to do is, okay, I want to find out this length of this thing. Oh, okay, sorry. The next thing I want to use is this. I want to get this radius of the Balmer line. So I will take my 1527.533, and here this lambda into delta lambda divided by this. So I have my value, right, the continuum value, which is 2.8 into 10 power minus 29, right? 2.8 into 10 power minus 29. But our answer here is in joules. This is given for ergs per second. So we will convert this ergs per second into joules per second and convert this to get the value of the radius of this broadline region, right? And then once we have R, we are going to take F is equal to 3 by 4. We will take R is this value we get from here, and B squared, we have B squared from our spectrum, and G is the gravitational constant, right? So using all this, we finally get our results, which is this. I'm just jumping this. I'm not doing this because we are falling a little short of time, but I'm sure you can substitute in those formulae and you will get the values. So the radius of the broadline region comes to be 98.8 light days, which is 2.56 into 10 power 15 meters. The velocity we had got is 6.6 into 10 power 6. And the mass of the black hole you will get is 1.28 into 10 power 39 kgs. Okay. Now we know that the mass of the sun is 1.99 into 10 power 30 kgs. So I will divide 1.28 into 10 power 39. I'll divide it by 1.99 into 10 power 30, and I get this number, which is going to be 6.43 into 10 power 8 m sun. That means we find that for the source 3C273, the mass of the black hole is 6 into 10 power 8 this thing. So it's about 600 million times the mass of the sun. So I'll pause just now over here. I'll take a few questions and then I'll proceed with the classification. But I can see there are some questions. So let me see. Okay. Yes. So I hope everybody figured out how do we do this. I'm sorry, I skipped this calculation part, but basically you just have to substitute it into this formula. So you will get the radius of the broadline region in light days, which I showed you was 98.8 you will get. We'll convert that to SI units, right, in meters, and then when we substitute here, we'll have to put this in SI units, which is in meters. We put our velocities also in SI units. This is 3 by 4, and gravitational constant also you'll put in SI units. And that's how we got the mass of the black hole. So I'm leaving that to you all to actually calculate and get the mass of the black hole. Meanwhile, please let me know if anybody has any doubts about what we just did. So I'm looking at the chat window to basically see whether this is clear. So you see that just using that plain H beta spectrum, right, we are estimating the mass of the black hole, right, for this source, which is 3C273. And similarly, if you have spectroscopy of stars, or in the bloodline region or towards the center of this of an AGN, you can actually use that to find out the mass of the black hole. Obviously, we are approximating, we are taking Kepler's law, we are taking simple approximations, but you'll see, I'll show you this. That's interesting, that look over here, you see we got a value, we got this value for the mass of the black hole, 600 million mass of the sun. And now I'll show you that if you were to actually look at this, let's say mass of black hole in 3C273, you can see it's 886 million solar masses, while we got 665 million solar masses. So that's not too bad at all. For astronomy standards, such an answer is considered very good, because it's called order of magnitude, right? We have 600 million times the mass of the sun. This is 800 million times the mass of the sun. Like I told you, our FWHM estimation was very rough, right? We basically just roughly looked at the figure and tried to see what is the value of the FWHM. But if you were actually doing analysis, right, you will take that spectrum, you will use Python or something to do a Gaussian fit to that spectrum, and based on that you will get the FWHM, right? And therefore, obviously your answer will be better. But you can see that even with this, we got a not very bad value. We've already got 600 and something million solar masses, which is already a very good value, right? And I would think that that's a good estimate for astronomy standards. I will now stop this and again look for questions on the chat. If they are not there, I am going to continue with a little bit of my presentation. So the assignment is, here I have given you a list. I hope you can see my screen, right? Yes, you can all see my screen, right? So the assignment is that this is a set of AGN, right, for which the redshifts are given over here. And this is whether they have SDSS data, which is over here. You have already seen SDSS data yesterday as well as today. And you can find out the mass of the black holes for these, or you can do it for these, or there's another sample here of Seyfert galaxies. These are also active galaxies, and these are much closer to us, so you won't have to do too much of cosmological calculations for this, because you see the redshifts are much smaller, and these are other Seyfert galaxies. Again, it's written whether you have an SDSS spectrum or whether you're getting it from NED. So depending on whether you have to take, yesterday I showed you how to get SDSS spectra. Today I showed you how to get a NED spectrum. So depending upon where do you want to take your spectrum from, you can take your spectrum from wherever you like, right? SDSS or NED. And you can actually calculate the mass of the black hole for any of these things. So the assignment is to do that for any one source, right? Take any source you like and find it out for that source, right? I just wanted to speak for 2 minutes more. Spectroscopy of AGN is also very important for classification of AGN, right? To classify AGN, to know what kind of an AGN you are talking about, we generally do that with spectroscopy. So, we spoke about FWHM. Similarly, for spectral lines, we have something called the equivalent width. That means, supposing you had a spectral line which has a certain FWHM, right? Supposing here I draw a rectangle which has a size, the width is such that the area in this is exactly equal to the area in this. So the equivalent width of a spectral line is the width of the spectral line if it has the same area as that of the line profile. right? So this is the line profile which has some area. I now make a equivalent rectangle which has the same area, which is this, and that will give me the width. Okay, and that is what is called the equivalent width. So often in astronomy, sometimes we talk about FWHM, and sometimes we also talk about equivalent widths of spectral lines, right? That's a measure of doing it. Now obviously if you have an absorption line, the absorption line comes inside, and therefore the equivalent width is considered to be positive. For emission lines it comes down, and therefore it's considered to be negative. Okay. Now based on equivalent widths, these are the ratio of the equivalent widths of different spectral lines, right? So this is the forbidden line of oxygen, which is at 5007 angstroms, divided by the equivalent width of the beta line at 4861 angstroms, versus nitrogen 2 forbidden line at 6583, divided by equivalent width of hydrogen alpha line 6563. And if you actually plot AGN on a plot like this is called the BPT diagram, the Baldwin-Phillips-Terlevich diagram. Then what you can do is this plot can be used directly to actually classify AGN, right? So I'm not going to go into the details in this, but just to give you a flavor that the way you found out the FWHM for that spectral line, similarly you can find out the equivalent width of spectral lines, right? And then, like in this case, you see you're taking the ratio of the equivalent widths of two different lines, here and here in log scales, and this is actually used for classification. So if you want to classify an AGN versus an H2 region versus a compact object, you can do it like this. If you want to classify between a Seifert and H2 region and a liner, you'll do this. If you want to classify between Seiferts and liners, you take another set of spectral lines. So if you notice over here, these are all different spectral lines which are taken, and they can be used. Now we don't have the time now to do this kind of an exercise, but in principle, if you were to do a problem or work on something in AGN, the first step is to do something like this, because you're going to use that to classify your AGN, right? So to classify the AGN, you will have to do, these are called spectral diagnostic diagrams. That means the diagrams with which you can actually this thing. I should also mention that this plot is done by Lisa Cooley, who is a woman astronomer. She is now came out with these diagrams, which are very important and very basic diagrams in the study of AGN. If you do AGN, you have to do BPT diagrams for your sources. So here's another set of BPT diagrams showing you the different classifications, and I'll end with that, right? So fine, 3:30. I wanted to stop half an hour in advance before our closing time. So I'm stopping over here. I can take some questions, right? Okay. So Urvashi, we take 5100 angstroms because, let me just show you, 1 minute. If you remember, I said that the emission lines, they are overlaid on the continuum lines, right? So if you actually see, okay. So if we actually see, I hope you can see my TopCat window. I hope everybody can see my TopCat window. Yeah. It will come up probably. Can you see my TopCat? Not yet. Can you see it now? No? You can't see it?
Can you see this presentation?
No. Then I'll stop share and I'll share again and I'll do this. The problem is I'm sharing between many different things. That's why. Now can you see it? Now I think you can see it?
Yes, ma'am. We can see it now.
Yes, ma'am.
Very good. So you see, this was the spectrum we were looking at. So this is the continuum over which we have these, these lines. This spectrum is called a continuum corrected spectrum. Otherwise, your spectrum would have been slightly tilted. Like a black body spectrum, it would have been something like this. I think I showed you spectrum like that earlier, where you'll get it slightly tilted. In this thing, this is corrected for the continuum. Now, what happens is, you see this region is where we have these spectral lines. But we want to see the strength of the continuum near this line. But over here I can't do it for the simple reason that there are emission lines, right? And therefore I look for a region, right? I look for a region where the spectral line is not there, right? So you see, if I measure over here, this is an emission line, this is also another emission line. So I want to take a part which does not have an emission line. So I am typically taking this part, which is 5100 angstrom, because here there is no emission line. I want a region which is close to the spectral line which I am studying, but does not have an emission line, right? So who's that? Urvashi? Yeah. So I can't get the continuum from here because there's a line over here, right? There's a line over here too. I cannot do it from here. At 5100, I don't have a line. So this is the flatter value, which is the value of the continuum. Actually, this whole thing is the continuum value. So ideally speaking, if I were doing a linear fit, right? If I go on forms and if I say I do a linear fit, this is the value of the continuum, right? So actually you are seeing that even 5100 little down, or this fit is not good, but if you come a little down here, this is the value of the continuum. So I can slightly change it. I will reduce my C. I can make it. Okay, you slightly change it, you can get something, but this is my continuum. So I take 5100 because that's where there is no line, right? Otherwise here I have lines. I don't want a part which has lines, right? Okay. So Urvashi, I hope that answers your question. Anybody else with any questions? Yeah. Yeah. So in principle, I was telling you this because in principle, supposing you were doing your analysis using this line, right? Supposing you were doing it with this line, then you will look for the continuum somewhere over here. You're going to look for a region close to that line which does not have a line, right? You'll take something like this. You won't take this part because this seems to have some kind of a bump. So you'll take this part, the lower part, right? And that will give you the continuum value. Right? So depending upon, see, we looked at optical Balmer line, but you may look at some other spectral line, right? Depending upon the instrument. So for example, if now James Webb is basically doing it in the infrared. So James Webb is going to look at spectral lines in the infrared, right? Which are also very useful for AGN because there's a lot of gas and dust in that central torus region of the AGN. So in infrared, you will get a much better spectrum than the spectrum you are getting in optical. This source is particularly is a very bright source, 3C273. That's why it's such a nice spectrum. But that it's not always so nice. Yeah. Okay. So I think, are there any other questions? Maybe we can go to Mamta if Mamta wants to give people instructions as to what do they do now. The most important thing is to try out the homework and please fill the feedback form so that we know what you feel about what we are doing. Because we are doing this because we believe that some kind of training will help people, you know, to learn these tricks of the trade, right? These are not very easy things to know. And specifically, if you are into research, you will know these things. If you are not doing research into these things, you will not know that. So the idea of doing this training program was so that, you know, we give you a first-hand view of this. So for example, the first day was light curve analysis so that you see the exoplanet. Then we did photometry so that you understand what is photometry, what is the HR diagram. Then we did on dark matter yesterday, and today we are winding up with black holes. But I added on some amount of spectroscopy with AGN so that you get a feel of what is AGN spectroscopy. So the feedback form, I can show it to you. Let me share the screen, and I hope you can see my Chrome window. And in our Chrome window, we'll go to Google Sites. Yeah, this is our website, which is the website for Women in Astronomy, right? There we have our upcoming things, whatever you want. And over here, if you click over here, come down, you'll come to our session, which is the April one. And oh, sorry, what happened? Okay. Right. So actually, if you go to the main home page, you'll come this to the home page. This is the home page. I should have shown this to you, and you'll see various things about here. about the members, what all are we doing. Please read our magazine and newsletter, which is called Ensemble. You will find some nice interesting articles over there and good information. And if you click on upcoming events and seminars, you will find the listing of our event, which is over here, which is April 2022. Click here. Mamta, where is the thing?
Yes, so yeah, you have to go down. Yes, then here you click here for registration. So just above.
Okay, I click on registration.
Yeah,
okay.
that brings you to the training program site. So
Oh.
the black, yeah, the black part.
Okay.
And
Okay.
then if you
So
go
here you all
down,
can see, yeah. So here you can see all the thanks, Mamta. So here are the days. Today's will come over there. Here you have provide your feedback. Okay. So this is the link for the feedback form.
Anyway, I've
So
sent it also in the chat box, the link, so you can always click on the chat box and you'll get it there.
Yeah, so I'll put that on the chat box and I'll send that to them in the mail also. So this is the thing on the chat box. You see, we are basically looking for details like your age, your gender, position, and you know, we want feedback like, is 5 days good, or would it be better with 2 days or 3 days? Is 2 hours too long, or is it short? What are your suggestions? Do you think that it's a worth it exercise that we are doing? And what about assignments? Is it easy for you to do it, etc.? So we are basically trying to just get a feedback so that we know how do we plan things in the future, right? Mamta, over to you. You can talk to them. Now I'll stop sharing.
Yes, so I think it's going fine, and let us know your feedback, send your assignments, and if you need a participation certificate also, so let us know on the Slack channel, and that's it. Based upon your feedback, we will organize the new training program based upon the topics that you would like to practice. So I think that's the way we can go on. Based upon your feedback and the needs and your interest, we can frame the new training program and find suitable coordinators for that. Or we will always have Priya, because she's the one who handles the training programs. She's an expert in that. She does it so well, and she's very patient, so it's great. So yeah, so let us know if you have any questions. Otherwise, we will stop here. But we are very happy to answer any questions if you have.
And we'd be even very happy to, if any of you all want to talk and tell us something just now about what you feel about these programs, or what do you, is there something specific? Because we are, you know, live online with you. So if you want to tell us something, that would also be nice about whatever. Or you can add it in your feedback form as you wish. So, where is Urvashi gone? Because I was trying to keep a check of, oh, Urvashi's there. So we have 3 women and 1, 2, 3, 4, 5, 6 men.
It turned out to be the other way.
Yeah. Why can't we have a 50-50% participation at least? That would be nice. Okay, thanks, Vaidi. Thanks for your appreciation. Yeah, but thanks, Mudasir. But that's what we thought, that this should not be a closed women event, because, you know, men are not our enemies or something. So you are most welcome to this thing. But you just remember that the Women in Astronomy group organized such an event, so for the benefit of everyone. So I think we can wind up over here. I don't see any more comments. I think people are happy to be finishing 20 minutes in advance.
Thank you, ma'am. The sessions were wonderful. It was my first experience to such sessions.
Was it difficult to follow and do the hands-on stuff?
Sometimes, not every time, but it was uncomfortable.
No, because for example, if we are, you know, physically present, you know, I can walk around, look in the lab, see who's, you know, managing or not managing. But now when we are online like this, you know, there's absolutely no way I know what's on your screen, what's on your computer, you know. So it gets a little tricky with hands-on with online, right? Because that's why I keep asking in between that if somebody's getting stuck, tell me, because sometimes you may be stuck for a very simple reason, you know. It needn't be something so complicated, and if it can be sorted, then you can, you know, proceed without an issue. So yeah, thanks Rupali. Yeah. What about Urvashi or YB, Rahul? How is it to do online hands-on sessions? Is it easy or is it difficult? Okay. Okay, Shankar. Good. So Shankar, you're doing web designing, that's fine, but you can like what we've been trying to show, that a lot of astronomy can be even done, you know, if you, as long as you're computer savvy and if you can, you know, analyze some data, it's fine. So you can actually do some astronomy if you want to, right? There's not such a, you know, big wall between academics and other things. You can do it. You wish. Yeah, why be network problems? Yeah, that's right. Network problems, and then the problem is the network problems are on both sides. Even we have them while you have them. Everybody has them. So, yes, network is really a problem.
Yeah, it's a problem, but it is also very useful because you can reach out to people all over the world, right? He is joining from Africa, I guess, and you
I
are.
think he's from Nairobi, right? You're from Nairobi.
Yeah.
YB, you're from Nairobi, Rogers. Okay. Yeah, that's right. And then anyway, the recording is there.
Yeah.
So if people have a problem, that's there. Okay.
But it's a global platform, and it is allowing the students to interact with each other from various parts of the world. The idea is also to bring you together, bring all the international committee of students together so that they also learn from each other and they also get used to being together. You know, it's not like only a group of European students or Indian students or the students only in Africa, but everyone together. And how to be, I think, how to work in collaboration with each other. That's the whole idea we would actually promote via these training programs.
Okay.
So I think it's a good platform, even if there are certain internet glitches. Somehow it brings people together, it is inclusive, and it is diverse. And that's the way the community should go ahead and should get used to working with each others. Because international projects are usually projects with different countries, people working together. So if they are already working together at the student level, then I guess they're used to working also when they become professionals. All right, so thank you. I guess we see lots of good returns and feedbacks. That's great. And we will wait for your assignments and your feedbacks, and we will wind up over there. Is that fine for you? Yeah. Shall I stop the recording?
Yeah, we can stop. Okay, so see you everyone. Yeah, where do you send the assignments? The same place where you got the email from.